Welcome back to The Explainer, brought to you by Forge College. Let's jump right in. If you caught our previous lesson, Core Components of SVM Clients, you know we basically popped the hood and tore down the engine to see exactly what makes it tick. Well, today, as part of our From EVM to SVM track, we're zooming out a bit to look at architectural contrasts, SVM versus other client models. I want you to imagine blockchain client models like manufacturing floors. You've got your careful, custom, one-at-a-time craftsmanship, and then you've got your massive, multi-lane, high-speed assembly plants. We're going to see exactly how the Solana virtual machine stacks up against the rest of the industry.
Here's the blueprint for today's explainer. 1. Intro to client models. 2. Core architectural choices. 3. The transaction workflow. 4. Account locking under the hood. 5. State sync and APIs. And 6. Key takeaways. Let's get to it.
All right, Section 1, Introduction to Client Models. So if the classical EVM is this incredibly reliable single-file assembly line, the SVM is a massive multi-lane factory floor with hundreds of workers just going at it simultaneously. Which kind of begs the question, why not just build everything sequentially? I mean, it sounds way easier to manage, right? Well, think of sequential EVM execution like waiting in line at the DMV. You take a ticket, wait your turn, and the clerk handles one person at a time, whether you're renewing a license or just asking a quick question. It's very orderly, totally predictable, but man, it is a bottleneck. Parallel execution in the SVM, on the other hand, is like a frenzied but completely coordinated Formula One pit crew. Multiple mechanics are changing tires, tweaking wings, and fueling the car all in the exact same fraction of a second. It requires intense coordination and highly specific tools, but the sheer throughput, it's undeniable. Moving on to Section 2, Core Architectural Choices. Let's look at these specific engineering trade-offs that make this high-speed parallel processing possible and, what you actually have to sacrifice to get it. Take a look at the resources row here in our matrix. An EVM full node can honestly get by with moderate CPU power, relying heavily on persistent storage because, again, it processes sequentially. A light client, it barely needs any local resources at all. It just offloads the heavy lifting to remote nodes. But the SVM-style client, it requires heavy machinery. We're talking massive RAM and blisteringly fast disk speeds, just so it can pull parts off the shelves instantly from a million different directions at once. The absolute crucial takeaway here is that mechanically, the entire SVM architecture is hyper-optimized for concurrency and speed. So if you're an integrator or a dev transitioning from Ethereum to Solana, you can't just copy-paste your infrastructure assumptions. It just won't work. You've got to design for fine-grained contention. You have to build memory subsystems capable of incredibly fast random access. The SVM will give you that sweet, low-latency confirmation, but it demands robust hardware and really smart engineering in return. That brings us to Section 3, the transaction workflow. Let's step onto the factory floor and track a single work order, a transaction, as it moves through the machinery. Every transaction hits 4 distinct stages. Step 1, RPC and gossip. Think of this as the loading dock. The transaction arrives, and we do quick pre-flight checks just to make sure the paperwork is filled out, signatures match, all that good stuff. We reject the junk early. In Step 2, the work order moves to the floor manager, the leader, who organizes the queue. Step 3 is where the real magic happens. The transaction hits the parallel assembly lines, acquires the specific tools or locks it needs, and executes. Finally, Step 4, ledger persistence. The finished state is boxed up, recorded in the ledger, and shipped out. Now, let's focus on that floor manager for a second. The leader or sequencer is a fascinating piece of the puzzle. Its entire job is to compose an ordered batch of transactions so they don't trip over each other on the assembly line. If 3 transactions want to update 3 completely different accounts, the leader groups them together so they can run at the exact same time. It's basically playing a high-stakes, real-time game of Tetris to absolutely maximize parallel execution. Section 4, account locking under the hood. So how does the factory actually prevent collisions? Like, if 2 workers need the exact same wrench at the exact same time, how does the SVM handle it without just crashing the whole system? Well, it uses some pretty straightforward scheduler logic. The system looks at a batch of pending transactions and checks a lock table. It's basically asking, hey, are the accounts you want to modify free right now? If the tools you need are free, you grab the lock and boom, you get to work immediately alongside everyone else. If someone else is currently using that account, your transaction is stalled and pushed back into the queue for the next round. It's a really elegant way to maintain deterministic outcomes while chewing through massive volumes. But, and this is a big but, here is the major trade-off you absolutely must understand. High throughput is virtually guaranteed for independent accounts. If everyone is working on their own distinct projects, the factory just hums along beautifully.
But what happens if a wildly popular NFT drops and suddenly 10,000 transactions are all trying to lock and modify the exact same smart contract account? Well, you get a bottleneck. Heavy traffic on a single account creates queuing delays. This means developers have to think very, very carefully about back pressure management and state design. You simply have to spread the load. Which leads us into Section 5, State Sync and APIs. Once the factory finishes a batch of work, how does it actually update the rest of the network? Well, you've got two main strategies here, and they represent classic engineering trade-offs. On one side, full snapshot replacement. This is literally like throwing out your entire filing cabinet and buying a fully updated one. It's conceptually super simple, very reliable, but it is incredibly intensive on your bandwidth and storage. On the flip side, you have incremental diffs. This is like just being handed the few new pieces of paper that need to go into your existing cabinet. It saves a ton of bandwidth, sure, but it requires much more complex verification to make sure those specific chunks are accurate. Ultimately, your recovery strategies and network capacity are going to dictate which choice your node operators make. Now, when you're interacting with these clients via APIs, you're inevitably going to encounter something called an optimistic RPC. Imagine calling the factory's front office to check on your order. The front office might tell you, "Yep, we accepted your order, it's scheduled on the floor." That right there is an optimistic response. It reflects locally accepted or leader-ordered state. But, and this is crucial, it does not mean the product has actually shipped and been finalized by the entire network. As a dev, you have to know exactly what guarantee your RPC endpoint is providing, because if you don't, your app's interface might show a transaction as complete before the blockchain has permanently finalized it, and nobody wants that. Finally, Section 6, Key Takeaways. Let's wrap this up. Let's bring all these moving parts together. I really love this quote from a source text. Map the guarantees you need to the architectural knobs described here. Choosing a client model or building applications on top of one isn't about finding the objectively best model in a vacuum. It doesn't exist. It's all about matching your specific project's needs, your latency, your finality, your resource costs, to the engineering trade-offs we've just discussed. So here is your rapid-fire recap, especially for those of you making the leap from an EVM environment. First, parallel execution is insanely powerful, but it demands aggressive hardware and resource provisioning. You literally cannot run this factory on a potato. Second, be highly aware of your state sync choices. They're going to aggressively impact your node's bandwidth requirements. And third, never, ever assume finality on an optimistic API call. Explicitly document your RPC semantics so your front ends behave predictably, even under heavy load. I want to leave you with this final provocative thought to chew on as you build. Will your infrastructure be designed to handle the blazing fast parallel chaos of the SVM, or will it be stuck waiting in line? Understanding these architectural contrasts is exactly what prepares you for our next lesson, where we'll dive into validator client diversity and operational implications. Thanks so much for joining me today for this explainer, brought to you by Forge College. To continue your learning journey and explore way more Web3-related topics, please visit our website at forge.college. See you in the next one.